All right, good morning, everyone. Just continue our conversation from Friday. So again, we started Gauss's law. So again, Gauss's law is a little bit conceptually difficult, but once we kind of get a handle on it, it's nice and easy to do, at least mathematically. So again, Gauss's law is defined as the flux through a three-dimensional surface is then equal to the charge enclosed inside of that surface divided by epsilon naught. Or mathematically, that's then the surface integral of the electric field dotted by the differential area, which again, surface integral here, the integral with a circle around it just means that it's the surface integral, or closed surface integral, meaning that you're integrating over the surface area of a closed three-dimensional object. And then Q enclosed, again, is the charge enclosed within inside of that object. Now, for us, Gauss's law says that we're actually using an imaginary surface, which is known as a Gaussian surface, which we get to choose based off the symmetry of the problem. So if we choose the correct symmetry based off of the symmetry of the problem, that means the electric field is constant everywhere along that symmetry, which means that this left-hand side simply becomes the electric field times the surface area, as long as we choose that symmetry appropriately. However, there are some caveats. So the first thing is Gauss's law doesn't always work, at least in this form. There are other forms of Gauss's law that we're not going to see in this class, but it doesn't always work. And examples are, I have two here. The left-hand side is, this is a rod, which has a charge and a finite length. So anytime my object has a finite length, Gauss's law does not work. So if I had a cylinder here, even though it does work with cylindrical symmetry, it has to be infinite in extent. And the reason for that is, again, if I was thinking about a point here, my electric field actually points off in this direction. Where at a point here, it only points radially in this direction. So to use Gauss's law, I have to use something which has perfect symmetry, which means it has to be infinite in extent, unless it's a sphere. The other one is the dipole that we talked about. So the positive charge and the negative charge. So this is our dipole. In this case, Gauss's law doesn't work because if I drew my Gaussian surface, so let me draw it in yellow here. Let's say I chose a sphere. Well, inside of here, I have a positive charge and a negative charge. Both have the same magnitude of the charge, which means for this thing, the total charge enclosed is simply equal to 0, which means that my flux is equal to 0, which means that the integral of the electric field dotted by the differential area is equal to 0. Now, does that mean my electric field is equal to 0? No, I've already drawn the electric field. It is certainly not 0. It just means that the total flux through this surface doesn't match the symmetry of the dipole, which means that I have as many field lines going out as I have coming in, which means the total flux is equal to 0. So we have to be a little bit careful with Gauss's law. So just because something is continuous doesn't mean I automatically apply Gauss's law. It has to have perfect symmetry to it. So if on the exam, if you saw something which is a finite length rod, and I asked you for the electric field, don't use Gauss's law. You have to use the other integral version that we use, which is the Coulomb's law. The integral of K integral dq over r squared. You have to use that one instead. So again, just be a little bit careful with Gauss's law. So Gauss's law has to have perfect symmetry to it, which means it has to be spherical, cylindrical, as long as it extends infinite in length, or planar. So good. So basically, all we're going to do today is pretty much do example problems. So that's all we want to do. So we want to get more practice with this by looking at more example problems. So this one says we have a sphere with a total charge Q and a uniformly distributed charge throughout the sphere, which has a radius of capital R. So we want to know what is the electric field inside and outside of the sphere. So now basically, when it comes to the inside of most materials, it's going to be one of three options. It's either going to be a conductor. We'll see an example with that, and we'll talk about the electric field for that. It's going to be uniformly distributed, like this one, or it's going to be a function. We'll do an example of that as well, so you can see all the differences, how we actually handle these things. But again, let's say, here's our sphere. This thing has a radius of capital R, has a total charge of Q, and we want to know, let's call this part 1, what is the electric field magnitude equal to when R is greater than capital R? So what that means is we're going to draw our Gaussian surface somewhere out here. So this R here is bigger than this R. And then 2 is when, what is the electric field, magnitude-wise, when R is less than capital R, which means we're going to draw a different Gaussian surface on the inside, which has a radius of little r. Okay? So you know, what is the electric field on the outside? What is the electric field on the inside? Let's do the first part first. So good. So we're looking for the Gaussian, or we're looking for the electric field outside of the sphere. Again, the sphere is a sphere, which means it has spherical symmetry to it, which means the best Gaussian surface to choose is the sphere which I drew. So that means then that Gauss's law becomes the integral of the electric field dotted by the differential area is then equal to the total charge enclosed divided by epsilon naught. Now, according to this gray sphere, how much charge is enclosed inside of that gray sphere? So how much charge of the sphere, of this sphere, is enclosed inside of this gray sphere? All of it, right? So capital Q. So we know the right-hand side then is simply going to be capital Q divided by epsilon naught. That's it. Because here we know that Q enclosed is equal to all the charge. Now, left-hand side, as we talked about last time, what happens is what? Since the electric field depends on the distance, everywhere across the surface of this, the electric field is simply equal to a constant, which means the left-hand side is simply going to be equal to the electric field times the surface area. That's it. So on the inside, or sorry, the outside, this says the electric field then is equal to Q divided by epsilon naught times the surface area of a sphere. But again, what's the surface area of a sphere? Dylan told us last time. Remember? Remember what you told us last time? Could be somebody else. Good, 4 pi r squared. So this is then simply equal to Q divided by 4 pi epsilon naught r squared. So that's the magnitude of the electric field on the outside. Great. Nice and easy. Now, let's do 2. Change the finished drawing. So 2, again, we have the same thing. So we have the integral of E dot dA is equal to Q enclosed divided by epsilon naught. The left-hand side is simply going to become E times the surface area is then equal to Q enclosed divided by epsilon naught. Everybody's okay with that? So again, the sphere still has spherical symmetry. So as long as I'm inside of the sphere anywhere, the electric field still has to be perpendicular to the sphere at all points, which means that this simply comes outside. So this becomes the electric field times the integral of the surface area, which is simply the surface area. So left-hand side stays the same. Nice and easy. Now the hard part is, what's the right-hand side? So again, Q enclosed means how much charge is enclosed inside of this sphere that I drew here. How much charge is actually enclosed inside of this guy? So in this case, this is what Q enclosed is. So what that means is, since this sphere here is smaller than the actual sphere, how much fraction of this charge do I actually have within inside of this sphere? Now here, this is where the trick comes in. So this is actually the hardest part of Gauss's law, is to determine how much charge is actually enclosed inside of here. Okay? Now what I have to understand, first of all, is what type of charge distribution do I have? We're told in this problem that it's uniformly distributed, which means that the charge per unit volume any place along this sphere is identically the same. Okay. Which means that, well, if I want to know the total charge enclosed, well, I simply have to know the charge per unit volume of the sphere times the maximum amount of volume I have enclosed. We're okay with this? So that means that Q enclosed is equal to the charge density times the volume which is enclosed inside of that sphere. Does this make sense? So if this has charge uniformly distributed throughout the entire thing, this is constant. So every per meter has exactly the same amount of charge. So if I know the charge density and I multiply by the volume which is contained here, then I know the total amount of charge. Okay? So let's write that on the next page. So I know that Q enclosed is equal to rho times the volume enclosed. Now, if this thing has a little r, how much volume is right here? So if I drew a sphere where the sphere has a radius of little r, how much volume is in that sphere? I.e., what's the volume of the sphere? What's the volume of the sphere? Good, 4/3 pi r cubed. So this is the charge density times 4/3 times pi times r cubed. Good. Now, but this depends on the fact that I have to know the charge density. Do I know the charge density? In a way, yes. What did I tell you? I told you it had a total charge, Q to it, and I told you it had a total volume based off the total radius of capital R, right? So remember that the charge density, by definition, is equal to the total charge divided by the total volume. This is the charge density. So for us, that's then equal to Q divided by the total volume, which is 4/3 times pi times capital R cubed. This is my charge density. So let's put these two things together. So this thing becomes then Q divided by 4/3 pi capital R cubed times 4/3 pi times little r cubed. What happens to the 4/3? They cancel. What happened to the pi's? Also cancel. So finally, this just becomes what? Q times the ratio of r, little r to big R cubed. So let's put all this together. So finally, this becomes Q enclosed, which is then Q times r cubed divided by epsilon naught times capital R cubed is all then equal to the electric field times the surface area. So the electric field then is equal to Q times R cubed divided by epsilon naught times the surface area times capital R cubed. What's the surface area? Well, again, it's a sphere, so it's just simply pi r squared. So let's plug that in. So finally, this becomes Q times R divided by 4 pi epsilon naught capital R cubed. Okay? Does this make sense? So as I said, the hardest thing here was simply determining what this was and remembering geometry. That was basically the hard part. Okay. Okay. Wonder why that's an R, not an R squared anymore. Remember, this is 4 pi little r squared. So that little r squared cancels off 2 of those. Okay. So that means that what? Just for fun, let's say if we plotted our electric field versus position, what happens in this case then is inside the sphere, it grows linearly until it reaches the radius of the sphere, at which it then has the maximum amount of electric field. And after that, it then decreases as 1 over r squared. So here's proportional r when it's 1 over r squared. So this is E versus R. Just leading off those two things. Plot of the electric field versus position. Let's do another one. So the next one says, we now have a conducting sphere which has a charge Q and a radius of R. What is the electric field inside and outside of the sphere? Same question, I'm just changing the type of material. So instead of having the charge uniformly distributed, this thing is now a conductor. So, once again, redraw our picture. So again, here is my sphere, which has a radius of R, charge of Q. And again, what I want to know is for part A, what is the electric field outside? So here's my little r. So I want to know what is the electric field when R is greater than capital R. And then for part B, I want to know what is the value of the electric field r is less than little r. Sorry, little r is less than big R. There we go. So this is my Gaussian surface. So let's go through all this again. Part A. Again, what we know is that we have the integral of the electric field dotted by the differential area. Again, we know our electric field looks like this. Which again means, let me do small steps like we did last time, dA points in exactly the same direction as the electric field, which means that dot product becomes 1. Which means that, again, since the electric field is constant everywhere along the surface, the left-hand side is the same thing as before, simply the electric field times the surface area. And that's all equal to Q enclosed divided by epsilon naught. Well, how much charge is enclosed inside of the red sphere? Capital Q again. So this is simply equal to capital Q divided by epsilon naught, which means the electric field is equal to Q divided by 4 pi epsilon naught r squared. Same exact answer as before. Nice and easy. So actually what this thing says is that what? As long as I'm outside of the sphere, it doesn't matter if it's conducting sphere or uniformly distributed or non-uniformly distributed, as long as the total charge is equal to Q, the electric field looks exactly the same. There is no difference. It's okay? Not too bad. What about part B? So part B, we're now looking at how much charge is enclosed inside of the sphere. Now, the key thing here is that this is a conductor. We talked about conductors at the end of the last chapter. What has to be true about the charge or the electric field inside of a conductor? Where must all the charge be when I'm dealing with a conductor? Is it at the center? Is it uniformly distributed anywhere in the inside? Or is it on the surface? Where is all the charge? It's on the surface, which means how much charge is enclosed inside of that green sphere? Nothing. Automatically, I know that Q enclosed is equal to 0, which tells me that the electric field is equal to 0 because I'm inside of a conductor. Conductors are the easiest things to deal with. Electric field must be 0 on the inside of a conductor. Something we learned at the end of last chapter. So that means all the charge must be on the surface, which means we don't pick up an electric field until we reach the surface, which means anywhere on the inside, an electric field must be 0. So for this one, if I plotted the electric field versus position, it must be 0 until I reach the radius. Then it must jump up to its maximum electric field, and then decay as 1 over r squared. This is the electric field for a conductor. Okay? So, point is, anytime you see a conductor, whether it's the exam or the homework or anything else, and you read that word, conductor, automatically you know that within inside of that thing, the electric field must be 0. That should be your only thought that you have. Don't worry about anything else. Okay? Is okay? Good. Let's do another one. 4. Let's change up the geometry. So this one says that we have a very long straight wire which possesses a uniform positive charge per unit length of lambda. So that's our line charge density. Also know, what is the electric field outside of the wire, far away from the ends? So let's look at this guy. So for this one, I have a straight wire. Here's my straight wire, has a uniform charge density lambda. Now, what has to be true about the electric field? Well, let's use this guy. This is the closest thing I have to a cylinder. So let's look at the shaft portion here. So here, what I know is that what? The charge here and the charge here, if I drew charges here and here, so let's say I put a charge here, so I have a positive charge here, and I have a positive charge here, What I know then is that the electric field on this guy points this way, this way, this way, this way, this way, and this way, while this one points this way, this way, this way, this way, this way, and this way, right? Now, if I superimpose this electric field on top of this one, what has to be true then about the magnitude of this one versus the magnitude of this one? They're the same because they're the same charge, right? Which means then that's what? The horizontal piece of this one and the horizontal piece of this one are equal and opposite, which means they cancel out from each other. Which means that the only direction that this electric field can point is like this. This is my electric field. Now, it's not only pointing out like this, but it's actually pointing out like this. Right? It's actually a cylindrical radially pointing outward. So here is my rod, it's pointing out everywhere in this direction. Okay? So this is this guy. My electric field is doing this. But coming out at us as well. Now, for the shaft portion here, what type of symmetry does this shaft portion have? Vanna White. You guys know who Vanna White is? Or am I telling you how epically old I am? Okay, everybody's okay. Good, so what type of symmetry does this thing have? Oh, I broke it, okay. So that might be a little easier. What type of symmetry is this? It's a, starts with a C. Cylinder, thank you. This thing has cylindrical symmetry to it. Good, so that means that, what, if I redrew this thing, let's go ahead and redraw it. So here's my line symmetry. This thing has cylindrical symmetry. So my electric field points this way, points this way. So that means that, since it has cylindrical symmetry, what type of Gaussian surface should I draw? A cylinder, right? So here, let's draw our Gaussian cylinder. So here's my Gaussian cylinder around this guy. My Gaussian cylinder then is going to have a radius of little r. So that's the radius of the end cap here. Now, the cylinder is a little bit more complicated because, again, Gauss's law says we have to integrate over the closed surface area of this object. How many different surface areas do I have in a cylinder? I technically have 3, right? I have this end cap here, I have end cap here, and I also have the shaft. Okay? So that means that for the left-hand side of Gauss's law, when we write down the integral of E dot dA, this has to be broken up into 3 different integrals. This is going to be integral over the end cap of the electric field dotted by the differential area, plus the integral over the shaft of the electric field dotted by the differential area, plus the integral over the other end cap times the electric field dotted by the differential area. Now, let's talk about the areas. Now again, what we said was, for Gauss's law, the end caps, or at least the surface area, dA points away from the surface. Which means that what? For this end cap out here, dA points in this direction. For this end cap down here, dA points in this direction. And for the shaft, see where my green, dA points off in this direction. This is my dA. So this is dA for the end cap, dA for the end cap, and dA for the shaft. Again, we know the electric field only points radially outward, so the electric field is doing this, which means this dA here, how does this dA then compare to the direction of the electric field? So if my dA is, or sorry, my RE is doing this, but my dA is out this way, I can do it like that. What's the angle between the two? 90, right? Because anywhere this thing's going like this is pointing out this way, it's 90 at all angles, which means that this is the same thing as the electric field times dA times cosine of 90 degrees. Well, what's cosine of 90 degrees? 0, right? Which means that I get 0 contribution from this end cap. What about this end cap? Well, in this end cap, dA points this way. The electric field is doing this, which means, again, I have 90 degrees, which means cosine of 90 is still equal to 0, unless they went and changed math on me, which that'd be weird. So that gives me no contribution, which means this entire integral here, I only get contribution from the shaft portion. That's it. So this tells me then that this is equal to the integral over the shaft of the electric field dotted by the differential area. Now, here, what's the angle between the electric field and the differential area? So one points this way, one points this way. What's the angle between the two of those? 0. What about down here? Here it's this way, here it's this way. What's the angle between those? 0. What goes on to 0? 1. So this is the same thing as the integral of the electric field times the differential area. Now, what can you tell me about the value of the electric field here versus the value of the electric field here versus the value of the electric field here versus the value of the electric field here? They're all the same. Which means that, what? Again, the electric field is constant, which means it comes outside of the integral. Right is great. So this thing finally becomes the electric field times the area of the shaft. That's it. Okay. Now, let me add one more thing on here. Let's say the shaft has a length of little l. So finally, Gauss's law says that the left-hand side is going to be the electric field times the surface area of the shaft must then be equal to the charge enclosed divided by epsilon naught. Now, the next question is, how much charge is enclosed? Well, I know this amount of charge is enclosed, right? Because if this is my Gaussian surface, the amount of charge which is enclosed is the amount which is inside of that cylinder. But what I also know is that this thing has a total charge of Q over L, right? That's what lambda is, which means if I want to know how much charge is enclosed inside of here, to find the total charge, what I have to do is take lambda times the length of that shaft. That's it. So what this says then is that Q enclosed is actually the same thing as the line charge density times the length divided by epsilon naught. So finally, this thing tells me that the electric field is equal to lambda times L divided by the area of the shaft times epsilon naught. Here's my cylinder. What is the area of the shaft? All I want to know is how much area is contained right here. Not the end caps, but the shaft itself. What's the area of the shaft? So it's going to be the same thing as the length of this times the length of this. Right? If this has a radius of r, what's the length of this? What do we call that? Call that the circumference. Right? What's the circumference of a circle? 2 pi r, great. This length is simply the length of the shaft that I told, which was L. Right? So in this case, my shaft is equal to 2 pi r times L. So let's plug that in. So this becomes lambda times L divided by 2 pi L times r times epsilon naught. This L cancels with this L. So finally I get lambda divided by 2 pi epsilon naught times r. So this is my electric field for a line charge. Okay? Let's do another. Skip that one for now, and I'll come back to this one. So this next one says, what happens if now we have a charge which is non-uniformly distributed? So we've seen what happens if we have a conductor. All the charge is on the outside, so we know the electric field has to be 0 because the total charge enclosed is 0 on the inside. We've seen uniformly distributed. That's simply the charge density times the volume enclosed. Well, what happens now if it is non-uniformly distributed? So here what I have is I have a hollow spherical shell, which carries a charge density of K, or K of some number, divided by r squared in a region of little a to little b. So that's the radius of our shell. So the inner radius is a, the outer radius is b. And I want to find the electric field in 3 regions. Inside the cavity, inside the spherical shell itself, and then outside of the spherical shell, and then finally plot. So let's kind of draw what's happening. So here, what I know is what? So here's my spherical shell. So here is the outer radius of B. Here is the inner radius of A, where between A and B is the actual object itself, which has a non-uniform charge density, rho, which is equal to K divided by R squared. So quick question, if all the charge is contained inside of the spherical shell itself, how much charge is on the inside? 0, none. What's the electric field on the inside? 0. Gauss's law says if there's no charge, there's no electric field. Life is great. So, 1, 2, and 3. So these are the 3 regions of interest. So for region 1, we automatically know that the electric field is equal to 0 since the charge enclosed is equal to 0. Done. Life is good. So here, that's if I drew my Gaussian surface to here. There's no charge enclosed. Electric field must be equal to 0. Now that would be different if I put a point charge there. If I had a point charge sitting at the origin, then the amount of charge enclosed would simply be that of the point charge. And that would give me the electric field. Is okay? Now let's look at 2. So 2 now, we're drawing our Gaussian surface somewhere on the inside of this shell. So here's my Gaussian surface. This has a radius of little r. Now, again, since this is a spherical shell, what type of symmetry do I have? Spherical, right? So that means the left-hand side of Gauss's law is simply going to be equal to the electric field times the surface area of the sphere. That's it. The right-hand side then is going to be equal to Q enclosed divided by epsilon naught. Now, in this case, Q enclosed is going to be a little more complicated because 2 things. One, this is a shell instead of being a solid sphere. And the other thing is because now the charge density is no longer uniform, it is not uniform. Which means that here, the first things first is we're going to have to consider what is Q enclosed. Well, Q enclosed then is going to be equal to the integral of the charge density integrated over the differential volume. So anytime I have a non-uniformly distributed, in this case, in the 3-dimensional sense, this is going to be equal to the charge density integrated over the volume. So what is this? This is going to be equal to the integral of K divided by R squared integrated over the differential volume. But here, I now have to determine where am I integrating my charge from. Right? Because I'm doing an integral, the charge is bound to a particular location, which means that I have to integrate over the bounds of where the charge actually is. Which means if I start here at the 0, there is no charge until I get to A. Right? This is where my charge starts, at A. So here, I'm going to integrate this from A. This is my lower bound. Because I have 0 charge contained inside of this cavity. So if I start here at the origin and I integrate outward, I can't get any contribution because there's no charge here. I can't start picking up until I get to the point where the charge is, and that's at A. Now I'm going to integrate from A to where this Gaussian surface ends. Where that Gaussian surface ends is the value of little r. So I'm going to integrate this from A to little r. Okay? Now, what is dV? So that's our next big question. Well, dV is going to be equal to what? The surface area of this shell, or at least of this surface that I drew, times the thickness of this line, which is simply equal to dr. Okay? So dV in this case is equal to 4 pi r squared dr. This is my dV. Where dr is the thickness of this guy. This is dr. So effectively what I'm doing is I'm cutting this up into a whole bunch of spherical shells. I'm putting all these spherical shells on top of each other, and I'm integrating over it this way. So good, let's put everything together. So this tells me that Q enclosed then is going to be equal to K, because that's a constant, integral 4 pi r squared dr divided by r integrated from A to R. Now, 4 pi is a constant. We're going to pull that out as well. So this becomes 4 pi times K integral. But I have an r squared divided by r. What's r squared divided by r? R, right? So integrated from A to R of r dr. I get to feel like a pirate when I do this. R dr. What's the integral of r dr? The integral of r dr. Besides a pirate. What's an integral? R squared over 2. Good. So this is going to be 2 pi k r squared minus a squared. Okay? So finally I can put everything together. So this tells me my electric field times my surface area, which is 4 pi r squared, is then equal to Q enclosed, which is 2 pi k times r squared minus a squared, divided by epsilon naught. Good. So now it's going to happen. Well, this pi is going to cancel this pi, right? This 4 is going to cancel with this 2 to make that a 2. So finally what we get is that the electric field then is equal to, I canceled the k instead of the pi. Okay, there you go. So this is going to be equal to what? K r squared minus a squared divided by 2 epsilon naught r squared. So this is my electric field. Anywhere inside of this spherical shell. Okay? Finally, part 3. Part 3 is now we're going to what? Draw this as our Gaussian sphere so that this is our radius little r. So what's the difference between 2 and 3? Well, it still has the same left-hand side. It's still the electric field times the surface area, which is still 4 pi r squared. None of this has changed. The only thing that's different is the amount of charge which is enclosed. The amount of charge which is enclosed now is still this integral, except what's the difference here? Am I going to integrate all the way out to little r, or am I going to integrate out to something else? So the question always becomes, where is the charge? Where does the charge exist? Well, according to our picture, the charge exists between A and B. Capital R, or sorry, little r here is greater than B, which means I can't integrate all the way out to R because now I'm overcounting the amount of charge because the charge doesn't exist there, which means I'm only going to integrate this from A to B. That's it. So here I just have to change the upper bound to B, which means when I recalculate this guy, the only difference is now this is going to be a B squared instead of an R squared. And I'm integrating this from A to B, which means this becomes B squared minus A squared instead of R squared. Which means the electric field only changes by this is now a B squared, but everything else stays the same. So for 3, we now have that the electric field is equal to K times B squared minus A squared divided by 2 epsilon naught R squared. So finally, the last thing we want to do is plot this guy. So how do we plot? So just give you a heads up on an exam, one of my favorite parts is always plot what you just did. And one of the things almost everybody screws up is the plot. They may get all this other stuff right, and then they just butcher the hell out of the plot because they decide, oh, I'm just going to make up crap. So how do I determine what this thing looks like? Well, I just follow what it is that I did. What I know is that for I, this thing has to have 0 electric field all the way out to radius of A. All I'm going to do is look at what I did. So in this case, what I know is this thing has 0 electric field until I get the radius of A. That's it. Well, in 2, what I know is that the electric field goes this way, which means that what? As R starts getting bigger at A, the electric field is still 0. But as it goes, this thing actually increases and does this until it reaches the maximum value at B. So I'm just reading off exactly what it is that I just did. So this thing now is just going to do something like this until it gets the radius of B. What does it look like after it goes to B? Well, all this stuff here is constant except for 1 over R squared. So this thing has to decay as 1 over R squared. And that's it. This is my plot. The plot is the easiest point. All you have to do is read off what it was that you just did and look at the simple R dependence. For I, there was no I dependence. So again, here there is no R dependence. Here, the R dependence tells you this part is growing while this one is decaying. That's why it actually turns over. And then for 3, the only R dependence is 1 over R squared. That's it. The plot is the easiest part. What's up, Molly?
Can you explain how you did the like how you determined that?
Oh, how I did that integral?
No, like just how you plotted that. You said like,
Oh, gotcha. Well, there's different ways you can do that, but basically what's happening is, so we have to overall look at what's happening. So if I ignore this A here, right? Let's see, how do I want to explain this? So I know this thing is increasing as kind of an exponential, right? So this is quadratically increasing while this one is trying to decay at the same time. Now, what's happening originally is when this thing is at 0, this part is more dominant, so this thing is trying to quadratically increase. But then overall, as it gets bigger, this part is going to become stronger because the number is going to become bigger versus this one, which is going to cause it to try to decrease downward. The other thing you do is just actually just plot it, make up some numbers and plot it that way. But yeah, so initially this thing is trying to increase quadratically, and then eventually this part's going to take over and want to get it to decay exponentially, or 1 over R squared. So it'll eventually have to turn around and do something like that. And the other reason is I've been doing it for a long time. But no, like I said, easiest way to do it is just use your calculator, make up some numbers, and then just plot overall what it would look like. Derek, what's up? Oh, so the last one, so let's go through each one. You mean from this one? Or the other ones before that? The other ones before that. Good. So the first one was that the electric field was uniformly, or sorry, the charge was uniformly distributed, which means that we actually don't have to do an integral in this case because, so let me write it kind of over here in the corner. Because if I wrote that the charge, let's do it this way, enclosed was equal to the integral of rho dV, but since this guy's equal to a constant, this comes out of the integral, which means this is rho times the integral of dV, but the rho times the integral of dV gives me exactly to this expression. So as long as the charge density is constant, it comes outside of this integral, and then this integral is simply the same thing as the volume enclosed. Okay? So conceptually wise, there's no difference. It just happens to be the fact that the charge density was constant. In the second one, we were told that it was a conductor, and we know that all the charge for a conductor has to be on the surface, which means if I'm inside, the electric field must be 0 by default. Okay. And then for the one we just did, so again, this one, we were told it had a hollow cavity here, and then, then all the charge was confined in here. So a different problem with this one would be instead of having a cavity, this thing had a non-uniform distributed charge throughout the entire thing. But again, I would have to tell you what the function of it looks like. Oh, so why is this not Q over R squared? Yeah, so this thing would be like the other ones. So for the other ones, we found that on the outside, the electric field was Q over 4 pi epsilon naught R squared. Effectively, that would be true here too, if I rewrote K here in terms of the total charge. If I did that, I would actually find that as well. So what I can also do is I can find the total charge, which is then equal to the integral of the charge density integrated over the volume from A to B, and then that would give me what K is in terms of 4s and pi's and all that different stuff. And then if I actually plug that in, what I would actually get is that the electric field is indeed simply this on the outside. Okay. So the answer to that is it's hidden inside of here, inside of K, because I didn't tell you what K was. But if I wanted to, I could make you find K by doing this, and then you would cancel everything out and get it that way anyways. So, okay, I understand the question. Is okay? So again, this is Gauss's law. It's always the same thing. The left-hand side is simply the electric field times the surface area. That's it. As long as I choose the correct symmetry, the left-hand side is always the electric field times the surface area. The complication comes into, one, what's the geometry? Do I remember the geometry? 4 pi r squared, 2 pi r, L, pi r squared, et cetera, et cetera. And then Q enclosed. The hardest part is determining what is Q enclosed. Q enclosed will come in one of 3 forms. Either be 0, because it's a conductor, uniformly distributed, which means I just have to find out the ratio, which is actually in there, or non-uniformly distributed, which means I actually have to do an integral. So the only integration part, which comes from Gauss's law, is if you have a non-uniformly distributed charge density. But for that to be true, I have to tell you exactly what the charge density looks like. That brings us to find it. Of course, we have no time to do it, but that's fine. Group assignments. So here are 3 extra ones for Gauss's law to give you some extra practice. The first one is a non-uniform distributed. So in this case, I want you to find the electric field inside the sphere, which carries a charge density which is proportional to the distance from the origin, which is given by rho is equal to K, where again, K is some constant times R. The second one is actually the problem we just did. So I'm going to give you a point of extra credit on the exam to go through what it was we just did to make sure that you understand it. Okay? Seems fair enough? I think so. The last one then is a coaxial cable, which means it's actually 2 cables on top of each other. So there's a cable running through the center, which has a radius of A, and then there's a coaxial shell around it, where that shell has a radius of B. But what it tells you is that the charge density on the shell portion is negative and cancels out the charge density, which is then carried on the inside wire. Which means that I have positive charge on the inside, negative charge on the outside, so how much charge is on the outside? 0. So that automatically tells you that the electric field outside of this coaxial cable is 0. Because the total charge enclosed is simply equal to 0. Okay? So finally, what I wanted to do is determine what is the electric field inside of the wire, what's the electric field between the wire and the shell, and what is the electric field on the outside. Well, we already know the electric field on the outside is equal to 0. So this is Gauss's law. Gauss's law is always a long problem on this upcoming exam. Always. Throwing at it. Everybody all happy. Like I said, Gauss's law is not difficult. Conceptually, it takes a little bit to get used to it, but once you're used to it, once you understand it, it is very easy. The hardest part is determining what is Q enclosed. That's it. Right? So, having said that, Wednesday, we'll then start potentials. Okay? So the last part right before the exam. All right. Gauss's law. Learn to love it. And for all you mechanical engineers, when you take fluids, you're basically going to be dealing with Gauss's law anyways. So you're not. We don't care.